As a child, magnets have always been a source of fascination for all of us. But did you know that these same magnets have an extremely important effect in the formation of stars themselves, just like our sun? I'm sure a lot of you must have seen this really famous picture of the Horsehead Nebula 1500 light years away from us. But have you ever seen this particular version of the image, where you see this weird lines superimposed on the image? Hello and welcome everyone to this new video. And in this video, I'll sort of take a tour of the Horsehead Nebula. In this case, I'll sort of show you guys the importance of the magnetic field lines that you can see in this image that has been published in this particular research paper. Magnetic fields actually plays an extremely important role in our entire universe, as in it controls the formation of stars. Allow me to explain you what do I mean by that. So as you know, our universe is filled with a lot of gas and dust. Now imagine if all of that gas and dust would convert into a star only due to the force of gravity. In that case, we would be living in a universe which would have more stars than we could ever imagine. But that's not the case. Don't get me wrong, we already have trillions and trillions of stars in the universe, but you would be surprised to know that the effective star formation rate is just 1%. And what is the reason behind such a low star formation rate? The answer lies in magnetism. Magnetism is one of the reasons why. There are other reasons, but this is an extremely important player which sort of controls the star formation rate. Magnetic fields sort of support against the gravitational collapse in a star forming cloud. Now what do I mean by that? Basically, imagine a cloud which is sort of threaded by magnetic fields, and these interstellar magnetic fields are caused due to charged particles moving freely in the interstellar medium. Now in such a scenario, as the gas sort of starts to collapse, due to the orientation of the magnetic field, it will sort of have an impact on the individual grains themselves. And as a result, they can sometimes work against the gravitational collapse, thereby slowing the process down, and in some cases, even not allowing the gravitational collapse to occur. There are other processes like turbulence, feedback from other nearby stars, so on and so forth, which also plays an important role. So as astronomers who are trying to study the formation of star, it is really important for us to understand the effects of each of these components, i.e. magnetic fields, turbulence, feedbacks, outflows, so on and so forth. Now trying to actually understand the orientation of the magnetic fields in these long distance cold molecular clouds is not trivial. It is actually quite a complicated process. But the fundamental mechanism behind that might be pretty simple to understand. Let me explain how. Okay, so let's imagine a cold gas of cloud made up of dust, and these dust are basically made up of some kind of carbon or silicate materials. Now imagine I have a source of strong radiation near that dust cloud. That source of radiation could be a young star core that has just formed, or let's say a strong bright star nearby. Dust by themselves are super tiny. They are actually in the micron scale. Not only that, these dust particles are also not uniform. They have certain asymmetries in them. Now if I apply force to a uniform body, now chances are, since the body is symmetrical, the force will be overall distributed. We'll have no net torque. But if the body itself has some asymmetry in it, and I apply some kind of an external force, it will experience a net torque. But this is exactly what happens in these gas clouds. If we have a nearby star that is really bright and young, and it's radiating away all of that energy, what happens is those energetic photons hits each of the individual dust grains, and as a result of the asymmetry in the dust grains, they soon start rotating. Since these dust grains are paramagnetic in nature, remember, paramagnetism occurs when we have unpaired electrons within the dust grains themselves. So as a result, as this dust grains start spinning up, due to the paramagnetism itself, it sort of induces its own magnetic field. Because remember, magnetism occurs when charged particles moves. The short axis of these dust grains tends to align with the magnetic field that's present. Slowly and steadily, a lot of these dust grains will start aligning within that particular region of the molecular cloud. Now the other thing that will also happen, the wavelength of the incoming photons is smaller than the size of the dust grain. It will sort of absorb that radiation, and then it will re-emit that radiation in the infrared side of the electromagnetic spectrum. The radiation is actually the direction of the long axis of the dust grains. Not only that, one special phenomenon that also occurs in this case is that radiation is polarized. So all in all, this cold molecular gas radiates in thermal polarized emission. So by observing the thermal polarized radiation of light, shifting them perpendicularly, we can actually get the orientation of the actual magnetic field present in that particular cloud. Light coming from star, for example our own star, basically has no polarization, which means the electrical and the magnetic components of the light are oscillating in different directions. What happens if I put a slit which only allows one direction of that oscillating component to pass? In that case, we get something called polarized light, or light which sort of oscillates in one particular direction. And that is the mechanism by which your sunglasses are made. So sunglasses only allow light at a certain polarization to come and hit us, thereby sort of lowering down the intensity of the light. So the magnetic field in the interstellar medium, threading through all these molecular clouds with all the dust particles themselves, acts as a sunglass, basically acting as a polarizer, which sort of polarizes the unpolarized light coming from that young star around it. So astronomers, using this particular fundamental idea, studies the magnetic field in the interstellar medium and molecular clouds. This is exactly something that has been done in this particular paper, where the two sources of radiation are a photodissociation region, and the second one is a starless core. A starless core is a dense star-forming region which has not yet formed a core, but has started to warm up again due to the gravitational collapse. The other, as I mentioned, is a photodissociation region. And these regions are caused when a young star emitting a lot of high energy UV radiation creates a shock-like structure around it, basically ionizing hydrogen to form H2. And interestingly enough, what happens in this case are that strong radiation from these sources sort of aligns the dust grains, allowing them to give off that polarized dust emission which we finally observe. And thereby, if you observe these particular region, you'll see that you'll get much ordered magnetic field as compared to the other regions of the cloud, thereby indicating that these might have some kind of a source embedded in them. Therefore, by looking into other wavelengths of light, we can actually understand as to what's going on within these particular molecular clouds. The authors in this paper have also measured magnetic field strength. These values are surprisingly very low in the microgauss region, as being shown on the screen. Now, the method for actually getting these values is quite complicated, and I will not include them in this particular video. So far, if you enjoyed this short discussion on magnetic fields in the interstellar medium and dust grains, do give a like in this video and leave a comment as to if you would really want to know how to actually find the true strength of that magnetic field. I'll catch you guys in the next video really soon.